Hello students, welcome to my channel Positron. Dear students, in my first few videos, uh, I'm covering the topics of mechanics. In the mechanics, I have made the videos on dimensional analysis, error analysis, problems regarding to error analysis, and some problems regarding to dimensional analysis and applications of dimensional analysis. Regarding to electrostatics, I have made the videos on charges and properties, electric Coulomb's law, vector form of Coulomb's law. Then in next video, I have considered the Gauss law and some applications in that video. And now today's topic is applications of Gauss law. Dear students, you know Gauss law is a very natural law. This is applicable only on the closed loop, right? If charge is enclosed in a loop, only then you can apply the Gauss law. If the charge is not enclosed in the loop, then you have to consider a significant, I'll say relevant loop at that, a relevant body in which the charge is enclosed. The first application I'm considering the field due to a straight wire on which charge distributed uniformly. Then let a thin wire is considering. I'm considering a thin wire on which charge is distributed uniformly. Let it is a very thin wire, right? On this wire, charge is distributed uniformly. If it is the positive charge, you know the electric field line begin from this charge, okay, and will be distributed in all the sides. And because it is a thin wire, how the thin wire can be made? How the charge can be distributed on the thin wire? Actually, a positive charge side by side you have put on this thin wire, right? Means why we are considering the thin wire? Actually, the charge cannot be put on each other, but the charges are kept just side by side, right? So due to one charge, if you will consider, the field will be like this, right, in all the directions, but not in that direction, because that field lines will be repelled by the charge, by the neighboring charges. Now dear students, this is the thin wire, right? On this, charge is distributed uniformly. Let it is a point P where you have to find out the field due to this charge. Now question is that, you know, we are studying the application of Gauss law by applying the Gauss law. We have to find out the field at point P due to charge distributed uniformly on a thin wire. Now dear students, you know the Gauss law is applicable only on the closed loop, right? So you have to consider the significant Gaussian surface here. Dear students, just I have told you that the field line will be distributed in this way in all the sides. This is a 3D actually. If you consider a single charge, then field will be like this in all that direction. In all the 360 degrees, the field lines will be coming out, right? But will not go along that wire. Why? Because just neighboring charges will repel the field line, right? So dear students, what I'm doing, I'm considering, I'm considering a cylinder which is having the radii r and length small l, right? In order to find out the field at point P, I have considered a cylinder of radii r, and this point P, you have to consider a cylinder of that dimension on which point P should exist. Actually, you have to find out the field at point P due to this thin wire on which charge is distributed uniformly, then you know, but for the application for applying the Gauss law, you have to consider a closed surface, but the surface should be such that on which point P exists. Let this point P is smaller distance away from this wire. That is why I have considered a cylinder of radii smaller. And so on this cylinder, this point P exists. And let the length of the wire is length of the cylinder is a small l. This wire has the infinite length, you can say, right? Dear student, now look here, three kind of surfaces are there. One is this curved surface. On this curved surface, the field line and area vector will be parallel to each other, right? If this is a curved, in this cylinder, this is the curved surface and these are the two plane surfaces. On this surface, area vector will be normally outward, and on this surface area vector will be normally outward. Area vector is always normally outward on the surface. Now, so here E and ds are parallel, but on these plane surfaces E will be like this, right? This electric field lines will go out from the field charges, and right, and area vector will be like this because the positive charge is distributed here. That is why field line will begin the charge and go to the infinity. In the case of negative charges, the field line will come from infinity to the charges. Now, electric field will be like this and area vector on this point like this. And in the same way, on this, let it is a plane P1 and this is a plane P2. On the plane P2, again you can see the field line will be like this, but the area vector will be normally outward like this, right? Now, dear students, you have find out the direction. The three surfaces are there, the two planes P1 and P2, and one is a curved surface. So, now how you can apply the Gauss law? Applying the Gauss law, dear students, what is the outcome? Gauss law is what? Integral E dot ds flux associated with a closed loop is equal to the 1 upon epsilon naught times of charge enclosed in that loop. 1 upon epsilon naught times of charge enclosed in the Gaussian surface. This is the Gaussian surface. The surface what I have said, that you have to assume the Gaussian surface, the relevant, the significant Gaussian surface. If it is a point charge, then the field lines will move like this. So the relevant surface, the relevant Gaussian surface, most significant Gaussian surface would be the spherical. In this way, the Gaussian, in this, when the charge is distributed on the thin wire, the best is to imagine the Gaussian surface as a cylinder. I have supposed a cylinder of length L and radius smaller. Now, dear students, what I have done, I have applied the Gauss law is the integral E dot ds is equal to q upon epsilon naught. Let lambda is the charge, you can say charge density or charge per unit length, because it is distributed on the wire, then we are considering charge per unit length. If it is distributed on the area, then what we will consider the charge per unit area. If it is distributed on the volume, then we will consider charge per unit volume. Now, dear students, how much charge will be enclosed in that? Lambda is the charge per unit length. So in the in L length, charge will be Q is equal to lambda into L. Lambda is the charge per unit length. So in the L length, the charge consisted will be lambda into L. Now, dear students, what I am doing, I am just dividing it into three parts. On plane P1, E dot ds plus on plane P2, E dot ds plus on curved surface E dot ds, and that is equal to Q is equal to lambda L upon epsilon naught. On plane P1 and P2, E dot ds is equal to on plane P2, E dot ds and that is equal to 0. Why? E is perpendicular to ds. You know A dot B is equal to AB cos theta, cos 90 is 0. On these two cases, E and ds are perpendicular, so it vanishes. And now, dear students, what happens? I am writing here. We are left with this third term only, that is integral E dot, over integral over curved surface E dot ds, and that is equal to lambda L upon epsilon naught. Dear student, on this, electric field and area vector are in the same direction, that is why it will become E ds cos 0, and cos 0 is a 1, you know, that is lambda L upon epsilon naught. Now, dear students, I am just erasing this one. Now, cos 0 is a 1, E is every point on the curved surfaces at equal distance away from the wire, and that is why E is constant at these points. At the surface of cylinder, every point is just equal distance away from the wire, and that is why E is constant at these points. That's why what happens, E I am taking out, you know, in the case of integration or differentiation, if constant is taken out and it turns out to be ds, that is equal to lambda L over epsilon naught. This is L actually. And now ds, the surface area of this. Surface area of this is what? Dear students, you know this is 2 pi r L. That is equal to lambda L over epsilon naught. And now it turns out to be LL will be cancelled. So E is equal to 1 upon 2 pi epsilon naught lambda over R. This is the electric field due to a straight, thin and infinite length wire on which charge is distributed uniformly. Electric field at point P, which is R distance away from the wire, E turns out to be E is equal to 1 upon 2 pi epsilon naught lambda upon R. Now just, I'm sure you people are following. Dear students, if do have any problem, do ask to me, do comment, okay? I will try to explain it in any other videos else. So we are moving to the next topic, next application I mean to say. Next is a dear student, considering a field due to thin plate of infinite area. Right? A very thin plate of infinite area like this. Right? This is a large plate, a plate of large area on which charge is distributed uniformly, right? Charge is distributed uniformly means sigma is the charge per unit area, you can say. Now, dear student, this is a book or a paper. Paper means it should be thin, only means large area, but not, you are not considering the volume. That is why the thickness will be very, very thin. So a large area, plate of very large area you have considered. Now you have to find out the field at the neighboring points, right? At points nearby to this place. So again, I am going to apply the Gauss law. In Gauss law, what is integral? Applying Gauss law, this is integral E dot ds. This is integral E dot ds is equal to q upon epsilon naught. Dear student, now the question is that what should be the significant Gaussian surface? What kind of Gaussian surface should we suppose here? Let point P is here, which is just a small r distance away from here, right? This is the plate, right? It's a big plate, a plate of large area, right? But a very thin, and a point P is here. Now at this point is a smaller distance away from the plate. We have to find out the field at point P. What kind of Gaussian surface we will suppose? Actually, we are supposing, dear students, we are supposing again a cylinder like this, right? A cylinder across, which is crossing. This is a thin plate, so cylinder is just crossing this is a plate and cylinder is just crossing the plate. Now look here, at these points, because plate is this, field line will move like this normally outward, and in this case area vector is also like this. So E and ds are parallel, and here at this side, this is the plate. At this side electric field is this, and area vector again is this, and area vector is parallel to the field. But on the curved surface, again field line will be like this, but ds will be like this, right? Because charge is this and electric field line will go out from the charge, right? But in the case of curved surface, the area vector will be like this. Because it is a curved surface, area vector will be like this, and charge is distributed on the plate, so field line will go either straight to left or right. So on the curved surface, this time E and ds are perpendicular. So you can say, just apply, break it. This is plate P1, this is plane P2. At plane, again I am breaking this Gauss law on plane P1, that is E dot ds, plus plane P2, that is E dot ds, that is plus over the curved surface, that is E dot ds, and that is equal to Q over epsilon naught. Now dear students, at curved surface E dot ds is equal to 0. Why? Because E is perpendicular to ds. Now that these at plane P1 E dot ds will be equal to at plane P2 E dot ds, and that is equal to E ds cos 0. Cos 0 is 1, E ds. Now E is equal at these points are same distance away from the plate, that is why E is constant, so E take out. And now ds is what? The area consisted by Gaussian surface. Let it is, this area is A, so E ds, that is equal to E into A. So dear students, I am just removing this. Now what becomes, at plane P1 it is E into A plus E into A at plane P2, and this becomes 0, and that is Q is what? Sigma is equal to Q upon A, charge per unit area, so Q is equal to sigma into A. So dear students, it is sigma A upon epsilon naught, or 2EA is equal to sigma A over epsilon naught. A will be cancelled, that is E equal to sigma upon 2 epsilon naught. So the field line, the electric field, due to uniformly distributed charge on a plate, on a thin plate of infinite area, E is equal to sigma upon 2 epsilon naught. Whether it is a positive charge distributed or negative charge distributed, magnitude of electric field works out to be the same, right? So E is equal to sigma upon 2 epsilon naught. We have considered the two cases we are discussing the applications of the Gauss law. First case I have discussed that how to find out the field due to straight wire on which charge is distributed uniformly, and second one is that how to find out the field at neighboring point to a plate having large area, thin, and charge is distributed uniformly. Let's move to the next case. Another case I am considering field due to solid sphere uniformly distributed, uniformly charge distributed. Dear student, in my last video I have found out, using the Gauss law, we have found out the field due to spherical shell. Now it is a field due to solid sphere we have to find out, on which the charge is distributed uniformly. Dear students, actually there are the three things we have to discuss. First, we should be very clear. First is solid sphere. Solid sphere means from center to the surface, material is there, is material, right? Hollow sphere is what? Let it is having the radii of this solid sphere. From inside of this solid sphere, a smaller sphere of radii are we have taken out. That is left a hollow sphere of external radii capital R and inner radii small r. Now what we have been left? We have been left with a hollow sphere of radii capital R and external radii capital R and inner radii small r. Actually, dear student, spherical shell is also a hollow sphere, but its thickness is very little. Its thickness is such that there is no question of external or internal radii. We do consider only one radii. Very thin means the material of which it is made is a very thin, like the plastic ball, the tennis ball, right? Now what we have to do? We have to find out the field due to solid sphere on which the charge is distributed uniformly. Case first, dear student, case first is when the point is existing outside, right? On this, let this point is P, and on this charge is distributed uniformly, right? It has the own radii small r, right? Whole charge distributed is Q, and a point P is smaller distance away from the center of the sphere where we have to find out the field. Dear students, in order to find out the field at point P, what I am doing, I am considering a sphere, a big sphere of radii smaller, on which this point P exists. This is the Gaussian surface. Again, I am using my words. Now, dear students, again you can say, if point is outside of the sphere, then you can imagine the field lines will move like this in all the directions, right? Yes. Now here E is in this way and area vector will also be normally outward. So E and ds are parallel to each other at every point. You can say if the point is outside of the sphere, then it seems that whole charge is concentrated at the center. Whole charge behave like a center, like a point charge that is kept at the center. What I am saying, if the point is outside of the sphere, solid sphere or spherical shell, then it appears that field lines comes out in such a way that it appears that whole charge is kept at is behaving like a point charge and kept at the center. In this case, now apply the Gauss law. What happens? Integral E dot ds is equal to total charge inside this Gaussian surface. That is means total charge of it. That is Q upon epsilon naught. Now, dear student, what happens? E ds, that is cos 0. E and ds are parallel at every point. You can find out at any point of the surface of Gaussian surface. That is equal to Q upon epsilon naught. Now, dear student, cos 0 is 1. E is a constant at each point of the surface because every point of the surface is a distance is smaller. So, E taken out, ds, that is equal to Q upon epsilon naught. Now, ds is what? surface area of this Gaussian surface, that works out to be 4 pi, radii of Gaussian surface is r, 4 pi r square, that is q upon epsilon naught. Dear students, we get the value 4 pi, just associate with epsilon naught, that is q upon r square, that is the Coulomb's law. Means, that is why what I am saying, that whole charge, if the point is outside of the solid sphere or spherical shell, then whole charge behave like a point charge and you can assume it to be at center. This is the first case when the point is outside of the sphere. Now second case, case 2. When the point is inside the sphere, now we have to find out the field inside the sphere. This is your sphere. Dear students, this is the sphere, has the radii capital R, charge distributed, charge is uniformly distributed, and this is sphere is a 3D. So here charge is distributed, uniformly distributed means charge per unit volume is a constant. Now let point P is here, which is small r distance away from the center, and we have assumed a solid sphere of radii small r, and this works out as a Gaussian surface. Dear students, here are the two cases, right? The first case is part A. If sphere is conducting, despite it is solid sphere, if the sphere is conducting, then whole charge will reside on the surface, right? Actually, dear students, if sphere is made of conducting material like copper, gold, silver, aluminium, then despite it is a solid sphere, the whole charge will reside at the surface of the sphere. So inside the sphere there will be no charge left, and that is why integral E dot ds is equal to q upon epsilon naught, but q, charge enclosed, will be 0, so you can say, so E equals to 0 in this case, right? If the point is inside of the sphere, when you have assumed the point outside, whole and Gaussian surface was such a big sphere, and this sphere, that charge was inside the Gaussian surface. But if it is made of conducting sphere and your point is just inside of the sphere, but in fact if it is conducting sphere, then whole charge reside at the surface of the sphere. In that case, inside there is no charge. This Gaussian surface will there no charge exists within this Gaussian surface. That is why field will be 0 in this case. Now dear students, part B is a very interesting. Part B is a what? If the sphere is non-conducting. Now this time sphere is non-conducting. Then what happens? Look here. Dear student, again apply the Gauss law, integral E dot ds. Let inside this, the total charge on this bigger sphere is q, and inside this the charge is q dash. Then it is a q dash or epsilon naught. At any point of this surface, right, field line will pass like this and area vector will be like this. So E and ds is parallel at each point on the surface of Gaussian surface. So it is a E ds cos 0, that is equal to q dash over epsilon naught. Again, every point of the surface of the Gaussian surface is equal distance, at a equal distance from the center. So E is a constant, take out, that is ds is equal to q dash over epsilon naught. Now dear students, what is important? The challenge is here to find out the charge enclosed in that Gaussian surface q dash. How you can find out? Actually, rho, I am writing charge per unit volume is a constant. Now, on total charge is q on the bigger sphere over the volume of bigger one is a 4 by 3 pi r cube. That is equal to, on the smaller one, total charge is q dash over its volume is 4 by 3 pi r cube. Dear student, charge per unit volume, either you consider the bigger sphere or this smaller sphere is the same, because charge distribution is a uniform. In the 3D case, you consider the charge per unit volume, that is remains constant. On the bigger sphere, charge per unit volume is that. On the smaller sphere, the charge per unit volume is this. Now 4 by 3 pi would be cancelled, so q dash, you will be left, q dash is equal to q small r cube upon capital R cube. Now dear student, just replace the value of q dash here, you will get the answer. Now what is E integral ds? Integral ds is a what? That is the surface area of that one is sphere 4 pi r square, a Gaussian surface, and that is equal to q dash is this q r cube upon capital R cube. This will cancel, it will be left with r. So E is equal to, and q dash over epsilon naught. So here is a epsilon naught also. This is the value of q dash over epsilon naught. Now E is equal to 4 pi will just write along with this 4 pi epsilon naught q r upon r cube. Now dear students, important that capital R is a constant, that is radius of this bigger sphere. So in this case, E is what? E is that is E is equal to 1 upon 4 pi epsilon naught q r upon capital R cube, means E is proportional to R, right? If you plot the graph, dear student, in my very first video, I have told you all, I have discussed with you all. If you want to be familiar with the physics, then there are the 3 tools which are instrumental, and you should have I don't say that you should have a deep knowledge, but you should have at least, you should be familiar with that 3 instruments, 3 tools. Like first is a graphical analysis. You should know the nature of graph. Just by looking the equation, you can just imagine that what kind of graph that will be. And second one is a calculus. Calculus, I mean the integral and differential, right? At least you should have a knowledge that you can solve the problem only. I'm not saying that you should have a very deep knowledge of that. And third one is a very important, that is vector analysis. Vector, I think you should be master of that vector, because you are studying the physics, right? So E is proportional to R. Dear students, now look here. When the point was just discuss these results, how you can plot the graph. This is right. This is a capital R. Now I'm plotting E versus R, right? Outside the sphere, E is equal to 1 upon 4 pi epsilon naught q upon r square. This is when small r is greater than r, right? Means when point is outside, then small r, that is distance of point P from the center, that is greater than the r. So E is proportional to 1 by r square. So and when small r is less than capital R, means inside the sphere, then E is equal to 1 upon 4 pi epsilon naught Q R upon capital R. Again, capital R is a constant, so E is proportional to R. So inside the sphere, you can say it is E proportional to R. If Y is equal to mx, straight line graph, slant and straight line inclined, m is a slope, right? So it is a E proportional to R inside the sphere, and outside the sphere, that is here E proportional to R and here E proportional to, inversely proportional to R square. Such a kind of graph you can plot. Okay. Dear students, I tried my best to let you understand the applications of the Gauss law. Next video undoubtedly will be the problems based on the electric field, Coulomb's law, and on the from the different combinations of the charge, how you can find out the electric field. Okay, so meet you in next video. I hope if you think that my videos are going to be beneficial, then again, from deep of my heart, I do say please and please like, share, subscribe, and do comment over the video, and must put bell icon so that you will be notified about my next video. Thank you.